Okay, so hi everybody. Thanks for listening in. Today we're going to talk about how we can use light to constrain the temperature, composition, and motion of individual objects. And this is, again, a representation of just how much information light can contain. And the way light contains that information is in terms of spectra, or more colloquially, color. We've already talked about how different objects in our solar system, which are basically we're looking at reflected light, have very different colors. Mars is quite red, Io is yellow, Neptune is blue. This actually reflects differences in their composition. Mars is red because it is composed primarily of iron, or its surface is covered in iron-rich material. We're essentially seeing rust. Io, by contrast, is covered in sulfur compounds, which are primarily yellow. So this is an example of how the color of objects reflects their composition. At the same time, stars show a variety of colors, but this mostly reflects variations in their temperature. Differences between red stars and blue stars has to do with those temperatures of those stars, at least the parts we can see. Now, the way we can quantify the actual colors that we're seeing here is using something called a spectrum. For any object that emits or reflects light, we can break up the different types of light, the different wavelengths, and make a plot like this. This is a spectrum. It is basically a plot of the brightness as a function of wavelength. And you can construct this of any object that you have light for. This is actually the spectrum of the Earth, which we'll talk about in class. The range of wavelengths here is quite broad, but over here on the left, you're seeing visible wavelengths. You have blues over here, reds over here. And the further up in the plot you are, the brighter you are. Now, in visible wavelengths, you can see there is some variation in brightness. The signal is highest at shorter wavelengths, which is blue. So Earth reflects a bit more blue light than it does red, which should make sense. Earth is on average blue. Now, in the visible range, there's maybe some trends, but not a lot of features. But of course, we don't just have to look at different wavelengths in visible. We can also look at different wavelengths in ultraviolet or infrared. That's what we're seeing here. And what you can see here are a whole bunch of structures, particularly dips. And these dips reflect the composition of Earth's atmosphere and surface. In particular, there's a lot of features here that can be attributed to water. There's a lot of information here. Now, we'll talk about the compositional aspects of the spectrum in a bit, but to start with, we should focus on something that's maybe a little simpler, how we can use spectra to look at temperature. And for that, it's better to look at the spectrum, not of the Earth, which is of course mostly reflecting sunlight, but to look at the spectrum of the sun itself. This is the same sort of plot, brightness versus wavelength. Just to say, wavelength can be measured in a variety of ways. This is in terms of nanometers, 10 to the minus 9 meters. But again, we have the region of visible light indicated here with colors. We have ultraviolet over here, shorter wavelength, and longer wavelength, infrared. Now, the yellow curve here is the solar spectrum. And what you can see is it has a very distinctive shape, which is shared with most stars. Its brightness rises and then falls. And there's a pretty broad peak in the spectrum centered around visible wavelengths. Now, this is not a coincidence. Human eyes and many animals' eyes evolved to be able to see in sunlight. So that kind of makes sense. Now, this generic shape, though, is typical of many stars and is reflective of a type of light generated by the fact that the sun is at a finite temperature. This is what is called thermal radiation. And this can be seen in stars. It can be also seen in hot things on Earth. If you take a piece of metal and stick it in an oven and heat it up, it will start to glow. And it glows with very distinctive colors. This is an example here that just looks kind of nice. If you start it off, it glows a dull red, which you can kind of see here. As you go to higher temperatures, it starts to glow brighter and develop kind of an orange or yellow hue. And if you make it even hotter, it starts to become extremely bright, appearing white or at least slightly blue. That is characteristic of objects that are heated. And it's a form of radiation that's due to basically the random motion of atoms and subatomic particles in hot material. Now, this type of radiation has a lot of properties that are basically just dependent on the temperature of this object. Now, at this point, I should make a side note to be a little clear about when I'm talking about temperature. I'm going to be talking about temperature measured in a kind of unusual unit known as Kelvin. Now, when we deal with temperature in the human world, we usually use Fahrenheit or Celsius because those are kind of useful scales for dealing with temperatures we experience in day-to-day life. Celsius is a bit more universally defined than Fahrenheit, but they're still kind of defined. So 0 is a cold temperature on Earth. Kelvin 0 is defined in an absolute sense. Temperature corresponds to the random motion of either atoms or subatomic particles within an object. Absolute 0 is when that motion stops. It's a sense of how cold you can make something. If you basically freeze everything so nothing moves, that's 0 Kelvin, which corresponds to roughly minus 273 degrees Celsius. Now, that means that 0 degrees here is about 273 Kelvin, 0 degrees Celsius, of course. And it works out that kind of typical room temperature is around 300 Kelvin. Now, stars and other objects that are glowing are 3000 Kelvin. And the nice thing about that is it gives you a sense of how much hotter they are. There's no offset. Something that is twice the kelvins has, in some sense, twice the motion. So, what turns out to be the property of thermal radiation is that the shape of the spectrum is basically set by the temperature. Now, for a certain type of idealized object called a black body, you can actually calculate this spectrum from first principles. That's what's shown here as nice, smooth curves. A black body is just an object that interacts with all wavelengths of light equally well. So there aren't any other spectral features due to composition. In that case, you get a spectrum that looks a lot like the spectrum of the sun. It starts low, goes up to a peak, and comes down. And the exact shape of the spectrum and the position of the peak depends on the temperature, which we'll get more into. Now, this is an idealized theoretical object, but real objects, especially those at high temperatures, match these predictions fairly well. For example, going back to this plot, the yellow-orange curve is the spectrum of the sun. The gray is an example of these sorts of theoretical spectra. Now, they're not exactly the same, but they match fairly closely. And this is true not only of, say, the sun, it also is true of other objects, like, say, that glowing metal bar that we talked about. So this model is actually fairly useful. And an important aspect of this model is that the temperature of the object determines the shape of its spectrum. Specifically, the location of this peak, which is where basically where the object produces the most light, depends on the temperature. If you have something that is very hot, the peak is in the middle of the visible range, or even in the ultraviolet. But as you go to lower and lower temperatures, the peak shifts to longer and longer wavelengths. And there's in fact a formula for that. The wavelength of the peak is a number divided by the temperature in Kelvin. What's nice about this is you can rearrange this to say the temperature of the object is a number divided by the wavelength of the peak. So if you can measure the location of this peak, you can figure out the temperature. For example, if you look at, say, this thing, it's glowing primarily in the yellow to orange part of the spectrum. So it's in this region of around 600 nanometers. That corresponds to a temperature of around 5,000 Kelvin, which is in fact the temperature of this rod. The sun is actually a similar temperature. It's around 6,000 Kelvin, which makes sense because its peak brightness is in the yellow part of the spectrum. That's why the sun looks yellow. And other stars, we can do a same game. The star Sirius turns out to be actually somewhat blue. Its peak in its spectrum shifts to shorter wavelengths. Shorter wavelengths correspond to higher temperatures. This blue light for the bigger star corresponds to around 9,900 Kelvin. On the other hand, Proxima Centauri, which is this red star right in the middle here, glows with a red light, indicating that the peak wavelength is shifted to longer wavelengths, indicating it's cooler, and it turns out to be corresponding to about 3,000 Kelvin. And you can even go beyond this if you're willing to consider the infrared. If you go to even lower temperatures than this, the peak shifts further and further into infrared wavelengths. And if we look at, say, planets like the Earth or this picture of Saturn, we can see that they glow at infrared due to thermal radiation. This is an image created from an infrared camera that was on board the Cassini spacecraft. Now, we can't see in the infrared, so I have to turn this into visible. The red radiation you're seeing here is actually on the dark side. You can see the lit side of the planet up here. This dark side is glowing, and it's glowing at a wavelength of 5,000 nanometers. This radiation is thermal radiation, but it corresponds to a much lower temperature, more like a couple hundred Kelvin. Now, these rings and the planet itself also show radiation at other wavelengths, but this is mostly due to the sun reflecting off of it rather than thermal emission. But it is true that if you can see the thermal emission of a planet, you can measure that planet's temperature. It just usually requires longer wavelength observations. So that's how we can learn about temperature from light. Talking about learning composition requires looking at this slightly differently. Again, all of these objects, Mars, Io, and Neptune, have different colors, not because they're different temperatures, but because they're made out of different atoms. Again, Mars mostly iron, Io mostly sulfur, Neptune various gases and particles, mostly partially methane. So what's happening here are different materials are interacting with different wavelengths of light. And we can see that happening all over the place. Another nice example is actually the sun itself. The overall spectrum of the sun is thermal, but there's slight variations in that, or slight features in it. This is another way to look at a spectrum. You're just splitting the light out. And so as you go across and down, the wavelength gets progressively shorter. So we start up here in red, go across, come to the next line, still red, keep going down, you get to yellow, you get to green, you get to blue, you get to purple. But on top of that general trend, you will notice there are dark bands. Those dark bands correspond to specific wavelengths of light that the sun just doesn't produce much light in. And they're very specific. There's wavelengths right here that plenty of light gets through, but right here, very little. This turns out to be due to the composition of material in the upper layers of the sun. And this happens also on Earth. Particular materials select out certain wavelengths. This can be done with lots of experiments. You take a light that emits a broad range of wavelengths and shine it through a gas. That gas will remove certain wavelengths. And if you look at the gas from the side, it turns out that what happened is that that gas scatters the light in other directions. So there's certain wavelengths of light that interact strongly with particular gases. And those gases each interact with different wavelengths of light. So again, this is just showing what happens if you look at this in terms of color instead of in terms of just a plot of brightness. If you send in a bunch of light, what gets scattered? Well, it depends if you're talking about a gas of sodium, hydrogen, calcium, mercury, or whatever. Sodium turns out to interact really well with certain types of yellow light. Hydrogen interacts more with purple and red light. Calcium, a different set. Each type of atom interacts with a different type of light. Why is this? Well, it turns out that the reason for this has to do with the structure of individual atoms, which means this process involves how atoms and light interact at a subatomic scale. This means it's due to quantum mechanics. So we're going to have to talk a bit about quantum mechanics now. And we can't obviously get into the full depth, but I want to talk to you a bit about how quantum mechanics gets involved via a very fundamental process in physics, which is energy conservation. Now, energy is something you've probably heard about a lot, but in physics, it has a very well-defined meaning. It is essentially the one quantity in a system that cannot change over time. This is actually built into its definition. The form of energy can change, but the total energy cannot change. So energy can change in form, but not in amount. Now, one form of energy is kinetic energy, energy of motion. Something moving has energy because it's moving. All other forms of energy, since energy can be transitioned from different forms, so all of those different forms of energy can be regarded as a potential to create motion. Light is one of those forms of energy, which you can see right here. This thing is glowing because there are objects inside this thing, subatomic particles, electrons, and atoms, moving around. Those moving around objects carry energy, and some of that energy can be turned into light. The hotter you make it, the more they move, the more light it can emit, and that light can go elsewhere and carry that energy elsewhere. So there's a clear relationship between energy and light, but there's an extra complication. The energy carried by light does depend on the brightness. The brighter something is, the more energy it carries, or the more energy the light is carrying. But the way energy works with light also involves the wavelength of that light. Shorter wavelengths carry more energy. Just to be a little more clear on that. Turns out you can do experiments where you shine light on certain materials like potassium and have subatomic particles come flying out. These are usually electrons. The speed with which those electrons come flying off depends on the wavelength of light going in. If you have blue light with a short wavelength, the electrons that get kicked off get kicked off at a high speed. They have a higher energy. You can change the intensity of this light and change how many electrons you kick off, but the speed, the maximum speed specifically, is basically set by the wavelength of the light. So that implies that there's something to do with the wavelength of the light that affects the energy. And you can do different experiments. If you increase the wavelength, the speed of these ejected particles goes down. And if you use a low enough wavelength, nothing comes out. That implies that there's some energy connection with the wavelength. And the way that is understood is terms of what are called photons. Basically, light comes in discrete chunks with a discrete amount of energy. That energy is inversely proportional to the wavelength. So a single photon, a single bit of blue light, carries a certain amount of energy, which is enough to knock an electron out moving at a fairly good clip. A longer wavelength green photon can knock out an electron, but it will move more slowly. Red light cannot knock one out. It can't give it enough energy to escape the metal. And no matter how much red light you put in, you'll not knock off the charges in this metal. So that implies that light has energy associated with it that depends on its wavelength. And this is important for how light interacts with atoms. Atoms, of course, are kind of complicated things. They are made out of several different parts: protons, neutrons, and electrons. There is a nucleus, which is where most of the mass of the atom lies, near the center, which contains the protons and the neutrons. This is a positively charged region, and it is surrounded by a cloud of negatively charged electrons that is much bigger. The electrons are what interact with other atoms because they're just distributed much more broadly. So it's the configuration and distribution of electrons that determines how this thing behaves chemically, what type of atom it is. But that configuration of electrons ultimately depends on how many protons are in the nucleus. Okay? The thing is, those configurations of electrons have some unusual properties that fundamentally do not make sense because they're very different from anything we can experience. Now, those electrons are held in place because they're attracted to the nucleus. So people often try to, particularly in astronomy courses, make an analogy between the electrons around a nucleus and the planets around the sun. This is a horrible analogy, but it's a useful one because I can at least give you a sense of why the atom is so weird. It is true that the electrons are held in configurations around the nucleus because they're attracted to the nucleus, because they're negatively charged and the atom is positive. The nucleus is positively charged. Just like all of the atoms are held in orbit because of the gravitational force of the sun. That's true. But there is an important difference, which is why we don't see these sorts of diagrams as often. The planets follow well-defined trajectories around the sun, but electrons don't follow well-defined trajectories around the nucleus. Instead, the probability that you can find the electron at a given distance from the nucleus is a fuzzy thing. There's a whole probability distribution of where the electron might be. You can't define a path that they follow. There is just a configuration of probabilities that they happen to have. So that's one important difference. The other important difference has to do with the configurations. For planets, the different configurations can be changed slightly. For example, if we wanted to put a big rocket on the Earth and we're willing to spend the chemical fuel to do it, we could use those rockets, convert chemical energy into motional energy, and cause the Earth's orbit to change. And we could cause the Earth to drift a little closer to the sun or a little further from the sun. And we could do that continuously. That is, we could make a change that's like a centimeter or a millimeter or a meter. I mean, all of this would be really hard, but we could imagine doing it. That's not how electronic configurations in an atom work. Each configuration of the atom, of the electrons around the atom, has a different energy, has a different energy, just like planets going around at different distances have different energies due to their moving at different speeds. But unlike planetary orbits, there are only a discrete set of allowed configurations that the electron can have for any given length of time. So you can have a fuzzy state that looks like this, or another state that looks like this, but nothing in between, at least not that can last for any amount of time. This is why you also see diagrams like this, which mark the configuration of the electron as a little circle around the nucleus, but there's only these discrete locations that are allowed. This is weird. You might say, well, why can't I create something halfway in between? It just doesn't work. And this has important implications because it means that there is only a limited number of ways that these electrons can change energies. They have to go between discrete states. So changing the configuration of electrons around a nucleus can only proceed in a few different ways. That strongly affects how it interacts with electromagnetic waves. An electromagnetic wave, a type of light, starts coming into this thing. If it has the right wavelength, has the right energy, it can take an electron in one of these states and turn it into another one, and thus be absorbed. The energy from that light, that photon, goes into the electron and it transitions. But it can only do that if the energy of that photon matches the energy difference between the two states. If it doesn't, that interaction can't happen. So there's only certain wavelengths of light that can interact with the atom, change the electronic configuration, and get absorbed. Similarly, when something is in one of these states and transitions to another state, it can release energy, but it releases a definite amount of energy that has a very specific wavelength. So when the electronic configuration changes, it only releases light at certain wavelengths. So those changes are, those specific wavelengths are what we are seeing here. These are the wavelengths that correspond to specific transitions between the configuration of electrons around the nucleus. So those are the only ones that are allowed. And which exact wavelengths they correspond to depends on the total charge of the nucleus. It depends on what type of atom it is, be it sodium, hydrogen, calcium, mercury, or whatever. So this is what we're seeing. And you do it in laboratory conditions, you can not change these very much, which is useful because it means when you look at spectra from other objects, you can figure out what you're looking at. For example, going back to the spectrum of the sun, there are these two dark bands here. Those two dark bands are at the right wavelengths to be due to sodium, indicating that there is sodium on the sun. This band and this band are due to hydrogen, indicating there's hydrogen in the sun. Turns out to be mostly hydrogen. There's also iron, helium, other elements. We can see those things in the spectrum. So that's how we can figure out composition. Now, for hot things like the sun made out of individual atoms, this is really precise because each atom produces its distinct chemical fingerprint in the spectrum. When you look at cooler objects, it gets muddier. First of all, in addition to atoms, you have molecules, which are just a few atoms linked together. But the way they're linked together is that there are interactions between the atom's electrons. Okay, this actually complicates the electron states. There's way more electrons involved. There's way more ways those electrons can change configuration. So the number of lines starts to go up. This, for example, is a spectrum of the atmosphere of Titan, which has very complex molecules in it, including methane, CH4, ethane, C2H6, hydrogen cyanide, etc. These don't have these do have individual lines, but they have many, many more. And you can see entire forests of lines here, which can quickly get confusing as they start to overlap on top of each other. They contain a lot of information, but pulling it out is harder. And if you go to solid objects, objects that are now many, many atoms all connected up, this gets even more complicated, and it turns these narrow features into what are called absorption bands, broad spectral features that you typically see when you look at the spectrum of solid objects. For example, here is a picture. Here are some spectra, again, brightness versus wavelength, of asteroids. All of these show a dip around 1 micron, and another dip around 2 microns. This is typical of silicon materials, things made out of silicon and oxygen. By contrast, these are the spectra of Saturn's rings, which also have a dip at 2 microns, but a dip instead at 1.5 microns, which isn't seen in asteroids. These dips are due to water ice. So identifying materials gets a little more tricky for solids, but it still basically works. If you have a dip at 1.5 microns, that's typical of ice. If you have a dip at 1, that can be indicative of certain types of rock. Cool. So this is the basic way we can use spectra to learn about composition. The last thing I want to mention is how we can use spectra to look for motion. For that, we go back to stars. These are spectra of 2 different stars. The green curve is the sun. The red curve is for the star Arcturus. What you have here is, again, brightness. And you'll see there are, again, it's fairly bright over this entire wavelength band, but there are narrow dips. The dips are due to these particular atoms. I'll point out we're only talking about a narrow range of wavelengths here from 882 to 885 nanometers. So, okay, these are dips due to particular elements, particular atoms. But you will notice the dips in the spectrum of Arcturus are different from the dips in the spectrum of the sun. Does that imply they're a different composition? Well, if it was just one dip that was different, that could be the case. Maybe there's things in Arcturus that aren't in the sun. But what you'll notice is these, for all three of the dips in this picture, the three strong dips, the Arcturus has a dip, but it's about 0.2 nanometers further to the right. That is inconsistent with a compositional difference, but instead reflects something about how Arcturus is moving relative to us. This is an example of what is called a Doppler shift. This is similar to how when you hear a siren go by, you hear a change in pitch. Turns out that the exact wavelength you see signals at depends on how that source is moving relative to you. And you can understand this fairly reasonably. If you imagine an object here that is producing a wave, we'll start with a blue wave, then a green wave, then yellow wave, then a red wave, and then a pink wave. These are just the crests of an electromagnetic wave. We're not indicating different wavelengths here. Those waves propagate in all directions equally. So the wavelength of this source of this wave is the same in all directions. Now, if instead you have a source that's moving top to bottom, when it produces this crest of the wave, it starts there. When you produce the next crest, it's displaced a bit. And as you go further and further along, you get this effect. The crests of the waves get bunched up in front of the object and spread out behind it. This is the Doppler shift. The wavelength of light, from behind the object is stretched. The wavelength towards the object in the direction of motion is squashed. And furthermore, the amount by which it's squished or squashed, the change in wavelength, is just the wavelength times the ratio of the speed of the source to the speed of light. So if you can measure this change in wavelength, you can figure out the speed of the source. It's just the speed of light times the change in wavelength over wavelength. So what we can say is this shift is probably because Arcturus is moving relative to us. And we can even calculate how fast it's moving relative to us. The shift is about 0.2 nanometers out of about 884 nanometers, just looking at this pair. Works for the other ones as well. So the change in wavelength divided by the wavelength is 0.0002. Okay, that means that Arcturus is moving at 0.0002 the speed of light. Now the speed of light is 300,000 kilometers per second. Multiply that by 0.0002 and you get 60 kilometers per second. So Arcturus is moving at 60 kilometers per second relative to us. Note, Earth moves at 30 kilometers per second around the sun. So that's not necessarily unreasonable. So, and the thing is, this is also useful because it allows us to see how objects are moving without actually having to see them move. And particularly, this is useful for galaxies because we can make spectra of different parts of a galaxy. This is a galaxy UGC 2936. It's a very nice disk. And if you take the spectra of different parts of the galaxy, you can make a plot like this. So here is the center of the galaxy. Here is the brightness versus wavelength, shown here as just darker colors or stronger signal. But this is the brightness, is the spectrum in this region. This is the spectrum up in this region. And what you will see is that the wavelength, so you see extra signal at particular wavelengths due to particular elements. I don't know which one exactly here, but what you can see is the wavelength shifts as you go from one side of the galaxy to the other. This is because the galaxy is rotating. Half of it's moving away from us, half of it's moving towards us. And with this sort of information, you can map out those motions, which is useful for understanding the dynamics of the galaxy and also for understanding the masses involved that are keeping those motions going. So, just in summary, we've seen how the spectrum of a source can carry information about its composition, its temperature, and its motion. The next thing we're going to have to talk about, and the last major topic of this section, is how we gather that light and the limitations on that based on our instruments, which are basically telescopes. Thank you very much for your time and attention, and I look forward to seeing you all in class.